All right, so welcome back to our channel here at OneClass. Again, my name is Joey. I'm going to be your math and chemistry teacher specifically for today. Again, if you're tuning in for the first time, thank you so much for watching. Here at OneClass, what we're doing is we're providing these online free videos for students at home and who are currently enrolled in school but cannot attend school because of school closures. What we're doing in this kind of series is we're answering frequently asked questions in both the secondary school subjects in math and chemistry, as well as the college and university level. So here at OneClass, what I'm doing, what my job here today is for me to verify these solutions provided by users across the world. And what we're doing is I'm going to teach you these concepts through asking these questions. So hopefully, what we're doing today is I'm going to divide the video up into kind of two parts. The first hour is going to be probably the first part of general chemistry in the United States, or equivalent to about grade 11 chemistry, or anything from grade 9 to grade 11. And the second part, in the second hour, I'm going to plan to answer questions that are typically found in university level, particularly second year organic chemistry. So without further ado, let's get started on today's problems. All right, so we have... First question here is, what is the molar mass of sodium hydroxide? So let's see. So I'm right here. So what is the molar mass of sodium hydroxide? So take a moment to think about this question. How do we find the molar mass? How do we find the molar mass first, or what is the molar mass? Here, what is the molar mass? And then we have to figure out, okay, what about sodium hydroxide? What is sodium hydroxide? How do I find the chemical formula? So let me just bring up the periodic table for you real quick. And then we'll go over, so remember the chemical here is sodium hydroxide. So how will we find the molar mass for this problem? What is the molar mass of sodium hydroxide? So take a moment to think about this question. Again, everyone in the chat, feel free to answer this problem or help me out with what to do in this problem here. All right, so what we have here is the molar mass of sodium hydroxide, right? We have to figure out, okay, what is sodium hydroxide? So remember, sodium hydroxide is comprised with its base first of all. We know that because of the hydroxide, right? So obviously it's made up of sodium, which here sodium is a metal, so it's gonna be on the left side of the periodic table. So Na here is our sodium, so I can say it's Na. And I'm going to write the charges here because we need to write the chemical formula. So it's Na plus, and then we have hydroxide. Hydroxide doesn't actually exist on our periodic table. Hydroxide is a polyatomic ion, so it's one of our special ions here. Hydroxide is represented by oxide, which is an O, the hydro, which is the H, the hydrogen here, and then it has a charge of -1. So Na plus and OH minus, the charge here is 1 plus, this here is a 1 minus, which means I will need one of each element or each polyatomic to satisfy the coefficient. So which means therefore my chemical formula here is NaOH for sodium hydroxide. NaOH. So once we have NaOH, what we can figure out is what is the molar mass, right? So when we talk about this concept of molar mass, remember how in order for us to calculate molar mass, we could use stoichiometry, but in this case we're not given mass or moles here, right? So in order for us to calculate molar mass, all we have to do is we have to look at our periodic table and find out the atomic masses of those substances. So I'm looking for sodium here. Sodium here is 22.99. Remember the bottom number here is the atomic mass, 22.99. 11 is the atomic number. Atomic mass is 22.99. So basically, I can break this down into, so I can say the molar mass, or big M, of NaOH equals, so the molar mass of Na, so the big M of Na, which is 22.99. So I can say it's equal to basically the M of Na plus the molar mass of oxygen, one oxygen atom plus the molar mass of a hydrogen atom, right? So I'm breaking this compound down back into its elements. So this here is kind of my formula to find molar mass. I'm just adding all the molar masses of the elements together. Sodium, like I said before, it's 22.99. So I'm going to put here 22.99. And this is in grams per mole, because that's what molar mass is measured in. Oxygen, we have a molar mass of 16, as you can see here, 15.999. I'm going to assume that this here is 16 grams per mole. And the hydrogen is obviously 1.008, right? So grams per mole. Hydrogen is our first element of the periodic table, so it has an atomic mass of 1.008. 1.008 grams per mole, which means therefore we can add all of these numbers up to get our total molar mass of sodium hydroxide. So let me do that for you. 22.99 plus 16 plus 1.008 would give me a grand total of 39.998. Or you can basically say 40 grams per mole, but I'll write down for 39.998 for you. 39.998 grams per mole. And if you were to observe significant digits, as you can see, I picked 16 grams per mole, so I can say, therefore, this here equals 40 grams per mole. And that will be our atomic mass, our molar mass of sodium hydroxide here. So let's see what they did here. The molar mass is given grams per mole for, he's given grams per mole or grams per mole. It is defined as the mass of any chemical element in grams divided by the amount of its substance moles. Perfect. So good concept here. We know that sodium hydroxide is NaOH, so mass of this is 22.99, 15.99 plus 1.0079. Therefore, our solution here is 39.996. 39.998 is close enough. You can round it to 40 because I have two significant digits. In this case, they took 5, so therefore they have to write 39.996. This here is a perfect solution. Perfect solution and analysis here. This here is our first question here is correct. Awesome. So let's look at our second question here. Let's look at our second question. So it's asking, is density a physical or chemical property? Let's talk about, so it's talking about this concept of physical and chemical properties, and we don't actually very see this much in grade 11 chemistry. It's more so in general science courses such as in grade 9. So let's look at this question and let's answer this quickly. So we have density. Is it a physical or chemical property? So if we want to define density, remember what is density in the first place? Density here, you can say that density here equals, in a mathematical equation, I'll say equals density equals mass, so an M divided by our volume, right? So this here is mass in grams divided by our volume. So basically how much something weighs per how much space it takes up per how much space it takes up over volume, right? So when we talk about this concept of physical and chemical properties, remember physical properties. What do we have for physical properties? We have, let's make a list. Actually, let's make a list of physical and chemical properties first. So physical, and then I'll just make like a T list or something like that, and then I'll make chemical properties. So physical properties, what are some examples of physical properties? Feel free to, like, if you know it, definitely chime in on the chat as to what are physical properties. So physical properties, we have obviously texture. Texture is a big one. It's anything you can observe with your kind of eyes, right? Color is a big one. Luster is another big one for metals, how shiny something is. We have, what else are physical properties? Texture, color. We have like the state itself, right? The state of matter is the physical property, right? State of matter. And yeah, those are just some decent examples of physical properties. And what about chemical properties? Chemical properties are when we try to react it with something. What properties are we using here? So, for example, combustibility is a good one. Combustibility, flammability. We have such. We have other like corrosive. Being corrosive is a chemical property. We have. I'm trying to think of indicators of chemical change. So like when it produces gas or if it changes color. These are all telltale signs of a chemical change using its chemical properties. So again, these things are chemical properties. So when we're talking about this topic of density, density is simply just a ratio, right? Like a density of water is one gram per 1 milliliter, right? So does that have to do with any of these physical chemical changes? Does weight, or if I rephrase this question, does weight actually have anything to do with a physical or a chemical property? In this case, no, because weight here it can change, right? I can change the weight of water or change the weight of, for example, my water bottle here, right? I can change the weight of this. I can buy a smaller water bottle or something like that. But can I change the texture or the color or the luster or the state of matter in this case? In this case, I can't, right? If I want to buy the exact same bottle in a different size, I could. Or but in terms of color, it would change the actual the physical property, right? Because if I look at it, it's a different bottle, right? It's a different bottle in terms of the color. So if you think about it, in terms of density, when we're talking about density or even weight, how much or the mass of something, it's neither a physical or chemical property because it's an inherent quality of the material itself. So it neither belongs in physical or chemical. It's actually I guess you can say it's not somewhere in the middle, but if anything, it kind of leans towards this physical property side. But density isn't really it's not physical property that we use to describe something. When we're describing physical properties of something, what we do is describe the texture, the color, the luster, the state of matter. We don't use weight because weight can change. Whereas texture, color, luster, and state of matter can't change. Copper will remain copper. It will remain hard, gold will remain brittle. Gold will remain shiny unless a chemical reaction happens. And the state of matter doesn't change unless I change the temperature, right? So again, these are things that don't change unless I change another thing. Density doesn't change. So in this case, they kind of describe what physical and chemical property is. That's good. So they're calculating some density of the matter here. So they kind of use this mathematical explanation to figure out the density of an object. That's okay. So I'm going to say density is a ratio between mass and volume, which has nothing to do with the change of state. Neither mass will be changed under any physical process or will volume be affected. So it can be stated that density is a physical property of the matter. So personally, like I don't like this answer because, again, it's definitely not a chemical property. So we can say that it's definitely not a chemical property. When we talk about physical properties, it's more so has to do with like what you can see with the property, because I care about what I can see, what I can feel. Again, taste would be a physical property, but we don't use taste in the lab. That's kind of the realm of physical properties. So I would say the density is, to be really, really precise, I would say density is actually neither a physical or chemical property because it's an inherent property. But I see the logic in terms of what they're trying to describe with density being a physical property, because it's something that's that takes shape and takes form, but then can also change depending on if I add more of that substance here. So I'm going to say that solution is I'm going to say I see the logic behind the solution. However, density does not. Let's see, density. Neither mass will be changed under any physical process, or will volume be affected. So you may say that density is a physical property. However, density is an inherent property of any substance. So it can also be said that it is neither or chemical property. Chemical property. However, if I had to choose between physical or chemical, I would also say that density belongs or is a physical property. There. Okay, so that's question 2. Okay, let's see. Question 3. It's asking, is sulfur a metal, metalloid, or non-metal? I think we did one of these problems before, maybe last week, but I'm not sure. So it says, is sulfur a metal, metalloid, or non-metal? It's asking also what's the family name. Okay, so in order for us to figure out if sulfur is a metal, a metalloid, or non-metal, all we have to do is look at the periodic table, right? And in this case, the P table here actually gives us a very, very nice indicator of our colors here. So all I have to do is I have to find sulfur, right? And sulfur belongs on our right-hand side of the periodic table because it's a you guessed it, it's a non-metal, right? So it says here, S here, in this green block here, it says it's all non-metals. Therefore, sulfur is a non-metal. If this was a test situation and I wasn't given these colors in terms of how do we figure out metals, non-metals, or metalloids, all we have to do is, the rule is, anything on the left side or the left side of the periodic table is a metal except hydrogen. So that's a very, very good kind of rule to kind of base off of, or and anything that ends in like IUM is a metal. You can think of it that way. Hydrogen, and these are the ones non-metals you kind of have to know. So hydrogen, carbon, nitrogen, oxygen, fluorine, phosphorus, sulfur, chlorine, selenium, bromine, and iodine are all gases and whatnot. They're all gases, or they're all gases. So basically, what we have to do is with these ones, we have to know that they exist mostly on the right-hand side of the periodic table. With hydrogen being the exception, obviously. And then for metalloids, it's kind of this little downward staircase. So boron, silicon, germanium, arsenic, antimony, tellurium, and astatine, they kind of make a downward staircase in our periodic table. These here are metalloids. So as you can see, here our nonmetals are kind of the green block here, and sulfur belongs in that green block. Also, we have to figure out, okay, what's its family name as well, because sulfur belongs in here. This is this is group 16. This will be the family name of sulfur, right? So in this case, it would be a chalcogen, or you can say simply just group 16. It would be its family name here. So I'm going to say that sulfur is a nonmetal and belongs in group 16. Sweet. So it says the concept is a periodic table. That's good. They talked about horizontal rows that are called periods, and vertical columns are called groups. And then they classified metals and nonmetals and metalloids. That's good. So that's what they did here, right? And sulfur again lies on the in the blue region here, the nonmetals here. So they actually even broke it down to like a even better explanation. So they talked about the electron configuration of sulfur. That places it here, and again, and then it says here it's placed in the third period and then 6A group, right? So you can say it's group 16. That's all good. And again, sulfur is present towards the right of the metalloids. Therefore, it is concluded that sulfur is a non-metal. It belongs to the oxygen family as well. All elements belonging to group 16 are called chalcogens. Right? So group 16 are called chalcogens, like I said here. So this here is my correct answer. So group 16 chalcogens is kind of the family or the group name, and sulfur is a non-metal. So this solution here is correct. And they have a very lengthy explanation actually, which is good. Great solution and logic. Okay, sweet. So let's look at this question 4. So it says table salt, NaCl, and sugar C12H22O11 are accidentally mixed. A 4.50 gram sample is burned and 1.0 grams of CO2 is produced. What was the mass percentage of table salt in the mixture? So let's look at our kind of question here. So we have NaCl, and we have sugar, which is C12H22O11, and they're mixed, right? Okay, that's fine. Accidentally mixed. A 4.50 sample is burned, and 1.80 grams of table salt in the mixture, right? So what they're asking, 1.0 of carbon dioxide is produced. What was the mass percentage of table salt in the mixture? So we're given our sample here. 4.50 grams of sample is burned, and 1.0 grams of calcium dioxide is produced, right? So and then it's also asking us what is the mass percentage. So in order for us to look at this question, we have to think about, okay, it's this chemical reaction of combustion, right? It's burned, right? So let's take a look at sodium chloride and sugar. Which one of these will burn more easily? Sodium chloride or sugar, right? In this case, sugar actually burns more easily. Sugar caramelizes at about 180 degrees. So in this case, we can say that a chemical reaction we can write is with sugar here, which is C12H22O11 plus oxygen gives us. I'm going to assume it's a complete combustion, and it gives us this equation here. So we have sugar plus oxygen, and burning it gives me water and carbon dioxide, which is good. I can balance this chemical equation as well. So there's 12 carbons on this side, which means I need 12 carbons on this side. So I'm going to write 12 here. Hydrogen, there's 22, and I only have 2 on this side, which means I need 11 hydrogens here. And finally, I have 11 hydrogen or oxygen, sorry, and then I have 24 oxygen. So I have 11 oxygens plus I have 24 here, which means I need 35. So I need 35 over 2 here. And if I want to get rid of the decimal, I have to multiply the entire thing by 2. So I'm saying this here is 2. This becomes 35. This here becomes 22. And this here becomes 24. Okay, so we have our balanced chemical equation for this problem here. It is, so we have 2, 35, 22, and 24. Okay, and it's asking a 4.5 gram sample is burned, right? And 1.80 grams of CO2 is produced. So let's in this sense, let's work backwards, right? So we have grams here. So let's make our kind of mass table. Mass, so this is mass, molar mass, and moles, right? So we have these types of things here. And so we're making our kind of table here. We have 1, 2, 3, and 4, right? And we're given our mass of CO2. So mass of CO2 is 1.80 grams, right? So what we have to figure out, let's figure out the molar mass of this CO2 first. So in order for us to do that, I simply have to do molar mass. So again, the chemical equation for this would be, I'll write this in blue, would be moles equals mass over molar mass. So therefore, molar mass. So therefore, I can figure out molar mass using the periodic table, right? So again, I have carbon, CO2, right? So C here is 12.01, plus, and I have 2 O2s, right? CO2. So I have 2 times 16 here to give us our molar mass of carbon dioxide, which is 44.01, right? So in this case, my molar mass of CO2 is 44.01. That's great. This is in grams per mole. I just don't have space here. So let me just write down, this is grams per mole here. super small. And then now moles is obviously mass divided by molar mass, like stated before. So I'm going to take 1.80 divided by 44.01, and that would give me the moles of my CO2 here. So this here is 0.041. So this is 0.04. I'll do 0.9 here. That's fine. And then what we can do is we can actually use kind of a mole to mole ratio to figure out how much sugar we have in the first place, right? So that's kind of how we find out the grams of sugar in the sample here. And then what we can do is we can take the mass percentage. So in order for us to do that, if we have 24 moles of, or the coefficient here is 24, and we have this is the moles of it in total, we can simply divide this 0.0409 by 24 to figure out how much moles, or 1 mole of CO2 is here. So we have 0.0409 divided by 24. So we have this is now 1.70. So let me write this down. This is 1.70. 1.70 times 10 to the negative 3. 10 to the negative 3. This is in moles, and this is per 1 mole, one mole of something, right? So once we have this, we have a coefficient of 2 here, right? So what we have to do is we have to actually multiply this number by 2 to figure out the moles of sugar in our compound. So if we multiply this number by 2, we would get we have 3.41. So this is 3.41 times 10 to the negative 3 moles. That's good. So once we have this, what we can do is work it backwards and work towards our grams of sugar here, right? So let's figure out the molar mass of this first. So the molar mass here, again, I have 12 carbons, 22 hydrogens, and 11 oxygens. So 12 carbons. I know my molar mass of the atomic mass of carbon is 12, so it's 12 times 12. Plus, I have 22 times 1, right? Again, my atomic mass of hydrogen is 1, so I'm multiplying that by 22. Plus, I have 11 oxygens times 16, which is the atomic mass of oxygen here, which makes a grand total of 342 grams per mole. 342 grams per mole. And if I want to figure out mass, I simply just have to multiply moles and molar mass together, right? So 342 times, this is 3.41 times 10 to the negative 3 would give me 1.16. This is 1.1666 grams of sugar, right? So now we know the grams of sugar in this case in our sample, which means we can find our table salt, right? Because we have our total mass here. Our total mass, oh, sorry. I'll do some blue. Because our total mass, or total here, equals 4.50, right? And this was a mixture of sugar and salt. But if we know our mass of sugar here, we can simply just subtract. If we want to find our mass of our salt here, simply have to take the total mass, 5.0 grams, minus 1.166, which is the mass of our sugar here, to finally get our mass of salt, which is simply equals 4.50 minus 1.166. This will give me 3.334 grams. And then from that, we can figure out the mass percentage, right? For the mass percentage, what we can, the mixture is simply, so the mass, I'm going to do it percent equals, again, it's going to be the mass of our NaCl, of our salt, over the total mass times 100%. This here equals, so again, this is 3.334 grams divided by the total mass, which is 4.50 grams, times 100%. And this entire thing will give us our mass percent of our problem. So this is 3.334 divided by 4.50 times 100%. 0.50 times 100%, and this will give us an answer of 74.0 74.09%. So this here is my solution for this problem, 74.09%. And then I can always go back to our significant digits to figure out how many significant digits I have. In this case, I have 3. So therefore, our answer here is 74.1% is our mass percentage of NaCl. So let me just scroll down and see if our answer is correct. So they have 58, which means our answer here, there's a discrepancy in our answer. So let's look at this problem here. So they balanced here, this is C12H22O11, and they balanced 22 and 24. Okay, that's fine. So I multiplied everything by 2, which is fine. Now 2.90 moles of CO2 is equal to, where did they get 2.09 moles? I'm very confused. Where did they get this number from? 2.90. They didn't get it from the question. They don't have, yeah, they didn't get that from the question at all. So again, I don't know how they got the mass of moles of CO2 is equal to, this here's the moles divided by, this is the mass? I'm not sure what they did here. Give me a second. So this 1.80 of CO2 is produced. And they're saying this is simply the moles. I think they meant to write the mass here, the mass of CO2 here instead of the moles of CO2, which means they threw off their entire answer. Because 2.90 is a number that they took out of thin air. I don't know where they got this moles here. Also, 2.90 moles divided by grams per mole does not give us moles here. The unit analysis here is wrong as well. According to the equation, the amount of sugar will produce is 1/12. That's fine. So they did this math perfect, and they multiplied to get grams, subtracted it, and they divided the 2.62 by the total amount, right? So this here solution is actually incorrect because of that first problem. They're incorrect. It's this question here. How did you get from the question? So I think you meant to divide the mass of CO2 by the molar mass of CO2 to get the number of moles in CO2. The logic for the rest of the question is correct. So again, this here's question is incorrect because I solved this problem using, again, I have the grams of CO2. I was given that in the first place. So 1.080 is grams of CO2. And I'm dividing that by, again, dividing by that by 44.01 to get our moles here. And in this first problem here, they already messed up here because this is 2.90 divided by 44.01. So this here is incorrect. Solution here is incorrect. All right, so that was question 4. That's a long question because, again, stoichiometry problems tend to be a bit longer because, again, you have to find the mass of something, the moles of something, the molar mass of something, and then you have to use multiple ratios to figure out the mass and molar mass of something else. So that was question 4. That's question 5. So it's asking, what is the molar mass of benzene? So molar mass of benzene. So in order for us to calculate the molar mass of benzene, I can actually draw out what benzene looks like, and then that might be able to help you out in terms of how to figure out what the chemical formula is. A benzene is basically a hexagon of carbons, right? So I have kind of this thing here. It's 1, 2, 3, 4, 5, 6. I have 6 carbons here, and then I also have, these guys are all bonded to 2 hydrogens each. So here is our, and then this here is aromatic. So this here, I'm going to put like a circle here. You don't have to know what aromaticity is in grade 11 chem, but it's totally fine. All I care about is the chemical formula. So in this case, I have I have this here is 1, 2, 3, 4, 5, 6. So I have 6 carbons, so C6, and then obviously I have hydrogens, right? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, right? C6H12. This is our chemical formula for mass of benzene, and then all we have to do to figure out mass of benzene is we have to just simply look at our periodic table, right? So we can say that the mass of benzene, or the molar mass of benzene equals the molar mass of our carbon 6, so 6 carbons, plus the molar mass of H12. Or I can simply just say, let me just do the math for you actually. So again, 6 carbons, we have it's 6 here times the molar mass of carbon here is 12 grams per mole, plus whatever, we have 12 hydrogens here. 12 hydrogens times molar mass of hydrogen is 1 gram per mole. Therefore, this here, 6 times 12 is 72. 1 times 12 is 12. 72 plus 12 here is 84. So this here is my molar mass of benzene. 84 grams per mole is my molar mass of my benzene. So let's check here. Molar mass, again, this is exactly kind of the same problem as what we did with our hydroxide, sodium hydroxide question in the beginning. So chemical formula is H6C6. This here is incorrect. Molar mass of chemical formula of benzene is not C6H, it's C6H12. So therefore, their molar mass is going to be wrong. Yes. And I can double check that, right? I can simply just Google what the chemical formula of benzene is if you don't believe me. Benzene, or it actually has benzene molar mass already. Or actually no, hold up. Benzene molar mass is C6H6. Oh, that's my bad. So it doesn't have. It's only bonded to 1 carbon? Oh, that's my fault. I guess my hydrogens are wrong. Sorry. It's bonded to, I thought it's bonded to 2. Give me a second. Let me just check this. Yes. Okay, I know why. So I drew this out because I thought that this was an alkene, but this is a cyclic hydrocarbon. So this is where I messed up here. Again, because it's cyclic here, I have like kind of a double bond that's going like this, and you can think of this double bond as going like around the cyclic hydrocarbon. So in this case here, it's only bonded to 1 hydrogen. So this here is wrong actually. My math here is wrong. Because hydrogen here is 6, so it's my fault. C6H6 here is the molar mass of benzene, which means this here becomes 6. I'll do my corrections in blue. 6 times 1 here is 6, not 12. And then this 72 plus 6 here is 78 grams per mole. So they actually got the solution correct. I got it wrong because I thought that it was C6H12 and not C6H6. So this is totally my fault here, which means this solution here is correct. My bad. And analysis. Okay, so another molar mass question here. So let's look at that. Another molar mass question here. It's asking number 6, what is the molar mass of phosphorus, right? So again, all we have to do is simply look at our periodic table to get this answer here. So it's asking what is the molar mass of phosphorus? So what is the molar mass of phosphorus? So again, take a moment to think about this. I'm going to switch to the periodic table to help you out. What is the molar mass of phosphorus? So as you can see, phosphorus here belongs in the non-metal section. So this is the right side of our periodic table here. And with it being on the right side, what it can do is so this is here is phosphorus. So P here has a atomic mass of 30.974, right? So 30.974. So P here 30.974 grams per mole. And in this case, so phosphorus is kind of a different it's kind of a unique atom, because what we have here is phosphorus can actually form it forms kind of like it forms kind of like a tetrahedral with itself. So in order for like a tetrahedral kind of compound, or it forms kind of like a pyramid, you can say. Like it has some sort of I'll try to draw it out here. It has like a triangle kind of base here, and then it also has this extends to a P, like so. So it's kind of like a pyramid, in this case here. In this case, phosphorus here has 4 atoms, right? And it's a bit harder for you to know, because in this case, in the scope of grade 11, you're not expected to know this geometry here. However, the scope of like university or like a grade 12 chemistry course, you would be able to expect that phosphorus makes kind of this pyramid shape here. So given that we know that already, let's assume we know that phosphorus here has 1, 2, 3, and 4. It has 4 phosphorus atoms, which means this is P4, right? P4, or you can say it's tetraphosphorus, right? Tetraphosphorus here is our chemical formula for phosphorus. And this here, if I want to figure out the molar mass, it's simply just 4 times our molar mass of phosphorus, right? 974. Therefore, this equals 4 times whatever that is. So again, 4 times 30.974. And this here equals 123.89. 123 point, I think it's 90 actually, 90 grams per mole. And this here is the solution here. So again, they did the exact same thing here. As there are 4 phosphorus atoms per molecule, the atomic mass of phosphorus is 30.97. That's good. And then they simply just multiply by 4. So in this case, it's the solution is this question is a bit harder, because it's like, what is the molar mass of phosphorus? We don't know what is it just asking us if it's P or if it's P4. Like we don't really know what the chemical formula is. So in this case, I would say solution is correct, but question is misleading, right? So it's misleading because we are not sure if the question is asking for 1 phosphorus atom, or you can say tetra or tetraphosphorus. Phosphorus, P4. In that case, then the solution or the molar mass changes. Molar mass changes. So solution, I'll say for this case, solution is correct. But again, we're not sure if it's asking for phosphorus or tetraphosphorus. But I'm going to say that here the solution is correct. Okay, number 7. What are the main ideas in Dalton's atomic theory? And how do they help explain the law of conservation of mass, of constant composition, and of definite proportions? Okay, so that's a lot. That's a jam-packed question. This is Dalton's atomic theory. Okay. And they're asking, how do they help explain laws of conservation of mass, of constant composition, and of definite proportions? Okay, so for this one question, I'm actually going to just look at the solution, because I really don't want to repeat myself in terms of explaining Dalton's atomic theory and then talking about law of conservation of mass, constant composition, and definite proportions for the sake of time. I'm just going to double check that they have they explain the law, the concept correctly. And as you can see, it's a very, very big paragraph, so I'm going to try to skim it for you. So it's asking, let's see, main ideas of Dalton's atomic theory are: elements are composed of small, indestructible particles named atoms. That's good. Every atom of a particular element has the same mass as the mass of other atoms of the element, and their mass is distinguished from atoms of other elements. A compound is formed when atoms combine in simple whole number ratios. So that's the law of definite proportions here. That's good. The law of conservation mass of constant composition and of definite proportions can be explained on the basis of Dalton's atomic theory because the matter is composed of atoms. So this here is our explanation. So it's saying, according to the law of conservation of mass is neither created nor distorted in a chemical reaction that remains unchanged, right? Therefore, the sum of mass of reactant and the sum of masses of the product will be the same. Good. So that's how they the law of conservation is exactly that. So this law can be explained as all atoms of elements have the same mass and no atom of any element is converting into another element during the reaction, then the mass will be conserved in a reaction. That's good. I can simply just use, I'm going to use an example here. I'm going to say I have H2 gas plus O2 gas yields water, right? So again, very, very easy. And as you can see here, I have 2 hydrogens here and 2 oxygens here. And then on the product side, I have 2 hydrogens and only 1 oxygen. So in this case, this actually doesn't follow the law of conservation of mass, right? I have 1 more oxygen here, right? That doesn't make sense. It means I have to balance my chemical equation, right? So in this case, this would be 2. I need a 2 here to make two oxygens and 2 hydrogens, right? 2 oxygens and 2 hydrogens. And now, here's 4 hydrogens here. And if I have 4 hydrogens here, I'm going to need another 4 here, right? Which is 2 times 2 makes 4. Which means this here is now balanced, right? 4 hydrogens, like so. So this here now follows my law of conservation of mass, right? So we have to balance our chemical equations. That's good. And then they're saying, according to the law of definite proportion, the mass ratio of constituents of a compound will remain the same in all samples of the compound. That's good. So if I have a sample of water, one molecule of water does not weigh differently than the does not weigh the same, or it has a mass ratio that's constant. It's always 2 hydrogens with 1 oxygen. That's the law of definite proportions. That's good. And it says, according to the law of multiple proportions, if 2 different compounds are made up of the same element, then the mass of that first element that combined with of the second element can be expressed as a ratio of a whole number, right? And that's what we're doing in this case here. If I have 2 elements to form 1 element here, the masses of them are the same, right? Because I have 4 hydrogens here, 2 oxygens and 2 oxygens here. And when 2 different elements combine to form different compounds, the masses of one element with the constant mass of another element in different compounds are always related to each other as a whole number. So again, 4 and 4, 2 and 2. This could be only possible if the matter consists of atoms. So long-winded solution, but solution is correct. Wish to see better formatting. Better formatting. Okay, that's good. And let's look at our question here. This here is complete the table of values for 4 aqueous solutions at 25 degrees. Okay, let me redraw this table here. So this is solution A, B, C, and D. I have a line tool, right? Yes, I do. That makes my life so much easier here. It makes your lives easier as well, because you can see what I'm writing here. So A here. So I have HOH. Oh, now my lines are just not straight. That's so awkward. Why are my lines not straight here? Whatever, it's fine. Okay, for the sake of this, it's fine. Okay, I have, this is, let me scroll up here. So this here is H plus OH minus, I realized I forgot a line here, unfortunate. So let me do that. Extend this line. Okay, hope you can all see that. Of pH and POH, right? Okay, that's fine. So for the first one, I'm giving the solution. So I'm gonna work. Maybe I'll work horizontally. So I'm given my concentration. These are in concentrations of my hydrogen ion here. This is H 8.3 times 10 to the negative 12 molar. So again, how would I solve for my me solve for my pH first. How would I solve for my pH of the solution here? So I would solve for my pH if I know, and I'm going to scroll down here, if I know that, I'll do some blue, pH again equals negative log of my H plus ions, right? So in this case, pH here equals negative log of, I have is 8.3 times 10 to the negative 12, right? So 8.3 times 10 to the negative 12 molarity here. And this here pH would now equal, so let me just plug in my calculator, negative log of 8.3 times 10 to the negative 12. This here will equal 11.08. So that here is my pH, which is great. So I can plug in my pH here. This is 11.08. Again, pOH is simply just pOH, or in this case here, pH plus pOH has to equal 14, right? So again, another useful formula here, and I'll do this in blue again, is the sum of pH plus pOH has to equal 14. So in this case, if my pH is 11.08, my pOH is simply 14 minus my pH, right, which is 11.08. So pOH would equal, this is 2.92, right? 2.92 would be my pOH here. This is 2.92. That's good. And then if I figured out my pOH, I can obviously solve for my hydroxide ions, right? So I can solve for my hydroxide ions using this here. So let me box the formulas I'm using here. So I use this one, I use this one, and I also use, I have this one last one I'm using. I'm going to use this one here. This is pOH equals a negative log of my hydroxide ions here. In this case, pOH is 2.92, right? So it's 2.92 equals negative log of my hydroxide ions. I need to move negative log to the other side, right? So if I move this to the other side, I would get hydroxide ions, or the concentration of my hydroxide ions in square brackets here, equals, this would be 10, the base is now 10, right? To the power of negative 2.92. And this here will equal, I'm going to shout 10 to the power of negative 2.92 would give me 1.20 times 10 to the negative 3. 1.20 times 10 to the negative 3. Which means this here is 1.20 times 10 to the negative 3. Sweet. So basically what we have to do is we do the exact same thing as we go down, right? As we go down the column here. So let me just draw it out for you. This is 5.0 times 10 to the 9. This is 3.37. This is 8.26. So again, the order doesn't really matter in terms of how you do this. I usually do OH with OH and pH with pH just for simplicity's sake. So let me do OH and pOH in column in solution B here, right? So again, I'm using the exact same formula. I'm going to use this one here. I told you I would box it for you. I would use this formula here to figure out my solution, right? So pOH would equal negative log of this number here, right? Of 5.0 times 10 to the negative 9, which is the concentration of our hydroxide ions. In this case, 5.0 times 10 to the negative 9 would give me 8.30. So I can simply put 8.30 in our pOH column. Whoops. 8.30. I can simply take 14 minus the pOH to figure out my pH here using this formula here. So let me use 14 minus the answer. 14 minus 8.30 would give me a number of, this is 5.70 for my pH, 5.70. And then with our pH, we can simply solve for the hydroxide ions right here, right? So again, I'm using this formula here, but then I have, let me do this in blue again. I have pH, which is now 5.70 equals to negative log of my hydroxide ions, right? Oops, sorry. Of my hydroxide ions. And I have to move negative log to this side, so H plus would equal 10 to the power of negative 5.70. Again, H plus would equal This here is 10 to the power of negative that, which is 2.0 times 10 to the negative 6. So this here is 2.0 times 10 to the negative 6. Yeah. Let me just double check something. Yeah, cool. So this here is correct. That's fine. And then all I have to do with the solution C again. I'm giving my pH, so let me solve for my. I can solve for my H plus or my pOH first. It doesn't really matter. Let me solve for my H plus here. So I'm taking the again 10 to the negative H plus 10 to the negative pH here would give me my solution, right? So I'm doing. Let me erase this to make room. But I can basically say that the concentration of H plus ions equals 10 to the power of negative pH, right? So in this case, my pH here is 10 to the negative 3.37 for solution C, as you can see here. And this here would equal 10 to the power of negative 3.37. This here equals 4.27, sorry. 4.27 times 10 to the negative 4. This is molars. And as you can now do, I can simply do 14 minus the pH to get my pOH. So I'm going to do that. 14 minus 3.37. So I would get 10.63 for my pOH. And simply I can take the negative log, or exactly, not the negative log, but I can take, I can use this formula here. And OH minus equals 10 to the power of negative pOH, right, to solve for that. This is simply just a rearranged form of this formula here. So again, the pOH here was 10.63, so 10 to the power of negative 10.63 would give me the concentration of my hydroxide ion. So if I do that on my calculator, I would get 2.34 times 10 to the negative 11 molars. And then finally for solution D, I'm doing the exact same thing. 14 minus the pOH would give me my pH. So 14 minus 8.26 would give me 5.74. And then I'm simply just doing, redoing these formulas here. I'm using these two formulas. H plus equals 10 to the power of negative pH. So 10 to the power of negative 5.74 would get me my answer, which is 1.82 times 10 to the negative 6 molars. And then finally, I can do 10 to the power of negative pOH, which is 8.26, to solve for my hydroxide ion. So negative 8.26 here to solve for my solution here, which is 5.4 or 5.50, sorry. 5.50 times 10 to the power of negative 9 moles. So this here completes my entire table of these solutions. So it's kind of wonky because I can't really see it, but let me just verify my answers real quick. This here is 1.23 times 10 to the negative 3. They wrote 1.20. Oh no, 1.23. That's good. 11.08, 2.91. I have 2.92. That's close enough. 2.0 times 10 to the negative 6. That's good. They gave you this 5.69, 5.70, and 8.30. That's good. 4.27 I have here times 10 to the negative 4. They have 4.2. That's fine. 2.34 times 10 to the 11. 3.37, 10.63. And then finally 1.81. I have 1.82 times 10 to the negative 6. They have 5.4. 2 times 10 to the negative 5. I have 5.5, 5.74, and 8.26. This here is my correct solution. So great solution. And analysis, because what they did was they also wrote the equations here, like I did, like so. So this here brings us to 1 o'clock. Again, thank you so much for watching our this hour of chemistry. Again, if you were in the live chat, thank you so much for participating and learning with me as well. I'm going to take an hour break, and then we're going to come back and do organic chemistry with you all. So again, as always, thank you for watching. Stay safe and stay healthy. Thank you so much.